Hello, everyone. So today we're going to be taking what we learned about how to determine the free energies for an individual reaction and essentially expanding this to more complicated ideas. So a lot of the times uh, we're not able to determine the free energy of formation for a species I care about from simple things such as the energies of formation of the relevant ions. Instead, we often have to go about more circuitous routes. So as I have more complicated thermodynamic processes, I'm often going to need to break these up into known steps. Essentially, I need to make a full thermodynamic cycle and figure out what I know and what I don't know, and piece together lots of little pieces of information to get the actual step I care about. So the most iconic example of this is what's called the Born-Haber cycle. So this is essentially a method of calculating the enthalpy of formation of an ionic solid from a series of individual measured processes. So say the reaction I might care about might be the free energy, the enthalpy of formation for sodium plus chloride to produce a sodium chloride salt. So again, this is more of an enthalpic expression, but you can use very similar procedures to determine free energy terms. So I might not be able to determine this number directly, but instead I might be able to piece together a series of steps that I actually do know. For example, I may be able to say, determine the vaporization of sodium, the bond dissociation enthalpy for chlorine, the ionization energy for sodium, and the electron affinity for chlorine, as well as what's called the lattice energy, to get me to this same point. It's also not uncommon that what you're trying to determine is the lattice energies, and you may know all of the other steps. But the key part of one of these cycles is usually I know all but one of these energies. And as long as you know all but one, you can essentially use the properties of state functions to essentially close the loop. Because, for example, I know that if I go this way, all of these energies should add up to being the same as this single step. So again, let's go ahead and work this as kind of an example for the enthalpy of formation of sodium chloride. So again, we can break this down into, say, sodium undergoing sublimation, which I have an enthalpy for, the sodium then being ionized, producing an electron, which I also am able to determine an experimental energy for. Pairing this with the bond dissociation enthalpy for chlorine and its subsequent electron affinity, all of which have known literature values. And then the last tricky one is the lattice enthalpy for sodium ion plus chlorine ions to produce sodium chloride salt. So again, by combining all of these numbers together, they should all end up adding up and being the same as my enthalpy of formation for sodium chloride. So this is actually a fairly useful sort of metric and a way to get enthalpic values. However, you can do the same exact idea and apply it to free energies or even entropies as well as enthalpies. And we can go ahead and say combine this idea with, say, the enthalpy, the free energy of formation, the free energy of formation of hydrogen and chlorine. So again, we can start with the same basic idea. If I'm doing the free energy of formation of my two ionic species, well, one way to go ahead and get to these ionic species is to go the complete other route. So I start with essentially the bond dissociation free energy for hydrogen, which we have a known literature value for, the free energy of the ionization energy, the bond dissociation free energy for chlorine, and again, the electron affinity free energy for chlorine. So again, the free energy equivalent of a lot of the same reactions we dealt with before. But here comes in the slight problem when you're trying to determine the free energies of, say, dissolved species instead of, say, solid complexes, because now I have to deal with the fact that I have to find the solvation energy of chlorine and the proton. However, because of its central role in so many reactions, including acid-base reactions, you can find relevant literature values for the experimental free energy of solvation for the proton of about negative 10,096 kilojoules per mole. So again, this is a lit value I can hunt down. And last lecture, we already determined how you can find the free energy of formation of essentially a fluoride ion, and it's very similar for the chloride ion. And again, the energy of formation of proton is always taken to be zero. So using the free energy of formation of chloride, I know that the free energy formation of HCl is going to be negative 131. So just like when looking at our Born-Haber cycle, I know every step except for one. And so what we can then do is rework our essentially combinations of our energies to isolate the free energy of solvation of the missing step by essentially saying, well, I can go ahead and say, if I start here and end here, it's going to be the negative value of my free energy of solvation of chloride. So essentially going here to here is going to be the negative of going from here to here. So hopefully that kind of makes sense. So what we can then do is take the negative value of adding together all of these individual components of the energies we provided on the last slide. And when you do this, what you find is that you have a free energy of solvation for the chloride ion of about negative 60 kilojoules per mole. And you're actually going to find that this is a fairly low number. And this actually is a fairly common feature of free energies of solvation. A lot of the free energy is going to come from the smaller ion, because it turns out that this proton is going to be very unhappy by itself. So it's going to be greatly stabilized, in fact, quite a lot, by being encompassed by nice supporting water molecules. The chloride, with its bigger electron cloud, is going to be much more stable on its own. And we'll talk more about these ideas of ion stability next semester when we get to play around a little bit with quantum mechanics. But again, hopefully this kind of gives you an idea of how you can essentially make thermodynamic cycles to figure out any missing piece of the puzzle for a chemical system. So next time, we're going to be moving on from simple thermodynamics to playing around with a little bit more non-ideality. Till then, take care.